Okay, welcome everybody to something called Gibbs free energy and spontaneity. And we're going to use this equation to answer the question, is a reaction spontaneous? And here's what we mean by spontaneous. Does a reaction run by itself? Or do we have to do something to get the reaction to run? Do we have to heat it? Do we have to light it on fire? Do we have to smash it with a hammer? Something like that. Okay? Here's the two conditions we're going to evaluate. First is delta H. This is change in enthalpy, and that's a big fancy word that means heat. And another word that we're going to use that is synonymous with energy, and that will be in joules or more often kilojoules. All right, so a reaction can be exothermic. Just got an email from Mr. Maliff, so you guys are probably all excited about that. A reaction can be exothermic, meaning that it gives off energy, meaning it loses heat to the environment, and that's what we would call a negative delta H. This is definitely more favored in the terms of whether or not the reaction runs. This is a definitely more favored arrangement, excuse me, because the universe doesn't really want to have to add energy to a reaction, right? So the universe isn't really into making reactions that require energy spontaneous. The universe isn't into like, for example, say stuff rolling uphill, for example. It's a good example of a reaction that requires energy. The universe is much more in favor of reactions that give off energy. So the universe likes reactions with a negative delta H, losing heat, giving off heat. All right? We should probably, since we're here, we should say that endothermic reactions, the ones where the delta H is positive, meaning energy is required, these are generally frowned upon. The universe doesn't, the universe doesn't favor these. Okay? Cool. So we like reactions that give off energy. The second variable that we're going to be looking at, this is going to be a new one, is called delta S. Depending on what textbook you use, and sometimes they just say S, this is something called entropy, otherwise known as disorder. We should put it this way. The universe prefers reactions that make a mess. The universe likes disorder. Okay, the universe is definitely in favor of reactions that are increasing the disorder, spreading things out. So the universe prefers reactions that make a mess. Okay? We're not talking energy here, all right? So all we're talking about is disorder. So in terms of how the universe works, the reaction of water as a liquid going to water vapor, this is definitely an increase in disorder because we're going from a liquid, which you can probably remember is, easy to contain. All right. You can, hold it in a glass. So a liquid is easy to contain, to a gas, which is difficult to contain. In other words, if you boil off your water into water vapor, you're not getting it back unless you've done it in some kind of controlled environment. So we should say that the universe prefers, or we should say the universe favors reactions that increase disorder, or this new word, entropy. And a reaction that increases disorder has a positive delta S. We like reactions that increase disorder. So another good example, going from fewer molecules to more molecule would be a good example of an increasing delta S. So a reaction like this is the reverse of something called the Haber process. We've got ammonia gas, and it is decomposing into nitrogen, which is a gas, and 3/2 of an H2, also a gas. This might require energy. You might have to add heat to this, a little delta H. You might have to increase the heat, and the universe doesn't favor that, but it definitely favors the fact that we went from one type of molecule to two. And if you want to add these up, we went from two molecules to, well, two different kinds of molecules. So this side is pretty ordered because you've got two of the same molecule floating around. But this side is pretty disordered, and the universe likes that too. So this reaction, we're not really worried about the delta H in this case, but we do know that this reaction would have a positive delta S. Okay? How are we going to use this? Now, if you were taking AP chemistry, I'd be giving you all kinds of tables that would give you values for delta H and delta S. But this is not that case, so we're going to keep it a bit more simple. Here's how this works. The equation for Gibbs free energy determines a reaction spontaneity. And it looks like this. Delta G, that's our buddy Gibbs, is equal to delta H minus T delta S. This is all one quantity. So this guy here, this is what we're going to call the free energy. Don't worry about what free energy means. We know that delta H is the heat, or you can also call that enthalpy. And let's remember that the universe favors reactions that have a negative delta H. So we'll just say negative delta H is preferred. Okay? Obviously, this guy T, this is going to be our temperature in kelvins. Let's erase that so you can see that T better. And here is our new disorder, which we now know is also called entropy. And a positive delta S is preferred. So what this equation is saying is that the free energy, delta G, is equal to the enthalpy in kilojoules per mole minus the quantity temperature times delta S. And since we know our kinetic molecular theory, or you guys remember kinetic molecular theory, that molecules are always in motion, it makes sense to say that, well, at higher temperatures, molecules are moving faster. So obviously, higher temperature is going to increase disorder. So this guy, delta G, here's how this works. Let's do it this way. We'll say a reaction is spontaneous. Whoops. A reaction is spontaneous when delta G is negative. Okay? In other words, when delta G is less than or equal to 0. Okay? So let's try this. I'm going to show you how this works. Delta G equals delta H minus T delta S. Let's try one. So here's a reaction. Now, this came right out of your textbook. So we have this reaction. It says that this is called ammonium chloride is dissociating into NH3. This is a solid NH3. This is a gas, and HCl, which is also a gas. Well, we also know that the reaction is clearly increasing disorder, but we don't have to worry about any of that stuff. We've got these three values. We want to calculate delta G. We want to find out if the reaction is spontaneous. Is it less than or equal to 0? It gives us a value for delta H is positive 176 kilojoules per mole. And it also tells us that delta S is positive 0.285 kilojoules. Sorry. Try in, ladies and gentlemen. Kilojoules over moles Kelvin. That unit looks weird for a reason. Okay? So what we want to do is oh, and also let's remember that it specifies that the temperature is 298.15 kelvins. Is this reaction spontaneous? Is this reaction, I'm going to abbreviate it, spontaneous? In other words, is delta G less than or equal to 0? So let's plug them in. We're going to crank this out. Delta G is equal to delta H, 176 kilojoules per mole, minus the quantity. We have a temperature of 298.15 kelvins times our delta S, which was 0.285 kilojoules per moles Kelvin. Now here's why that unit looks so weird, because kelvins are going to cancel. Okay, let's bust out our calculator. I have my fancy Texas Instruments emulator calculator, and if it works, there we go. And so what we're going to do is we're going to say positive 176, and we're going to subtract from that the quantity, 298.15 kelvins, times 0.285 kilojoules per mole Kelvin. Our answer is 91 kilojoules per mole. Is the reaction spontaneous? Delta G is 91 kilojoules per mole. No, it is not spontaneous. Okay, we're going to call that part 1, and I'm going to explain what we're going to do in part 2.